An intuitive explanation of Bayes' theorem, Part 5. Similarly, Popper's dictum that an idea must be falsifiable can be interpreted as a manifestation of the Bayesian conservation of probability rule. If a result X is positive evidence for the theory, then the result not X would have disconfirmed the theory to some extent. If you try to interpret both X and not X as confirming the theory, the Bayesian rules say this is impossible. To increase the probability of a theory, you must expose it to tests that can potentially decrease its probability. This is not just a rule for detecting would-be cheaters in the social process of science, but a consequence of Bayesian probability theory. On the other hand, Popper's idea that there is only falsification and no such thing as confirmation turns out to be incorrect. Bayes' theorem shows that falsification is very strong evidence compared to confirmation, but falsification is still probabilistic in nature. It is not governed by fundamentally different rules from confirmation, as Popper argued. So we find that many phenomena in the cognitive sciences, plus the statistical methods used by scientists, plus the scientific method itself, are all turning out to be special cases of Bayes' theorem. Hence the Bayesian revolution. Having introduced Bayes' theorem explicitly, we can explicitly discuss its components.
P a given x equals px given a, xpa, over px given a, xpa plus px given not a, xp not a.
We'll start with P a given x. If you ever find yourself getting confused about what's a and what's x in Bayes' theorem, start with P a given x, on the left side of the equation. That's the simplest part to interpret.
In P a given x, a is the thing we want to know about.
X is how we're observing it, x is the evidence we're using to make inferences about a.
Remember that for every expression pq given p, we want to know about the probability for q given p, the degree to which p implies q. A more sensible notation, which it is now too late to adopt, would be p, q less than, p. P, q given p, is closely related to p, q, p, but they are not identical. Expressed as a probability or a fraction, p, q, p, is the proportion of things that have property q and property p among all things. For example, the proportion of women with breast cancer and a positive mammogram within the group of all women. If the total number of women is 10,000, and 80 women have breast cancer and a positive mammogram, then P, Q, P, is 80 over 10,000 equals 0.8%.
You might say that the absolute quantity, 80, is being normalized to a probability relative to the group of all women. Or to make it clearer, suppose that there's a group of 641 women with breast cancer and a positive mammogram within a total sample group of 89,031 women. 641 is the absolute quantity.
If you pick out a random woman from the entire sample, then the probability you'll pick a woman with breast cancer and a positive mammogram is P, Q, P, or 0.72%, in this example. On the other hand, P, Q given P, is the proportion of things that have property Q and property P among all things that have P. For example, the proportion of women with breast cancer and a positive mammogram within the group of all women with positive mammograms. If there are 641 women with breast cancer and positive mammograms, 7,915 women with positive mammograms, and 89,031 women, then P, Q, P, is the probability of getting one of those 641 women if you're picking at random from the entire group of 89,031, while P, Q given P, is the probability of getting one of those 641 women if you're picking at random from the smaller group of 7,915. In a sense, P, Q given P, really means P, Q, P given P, but specifying the extra P all the time would be redundant. You already know it has property P, so the property you're investigating is Q, even though you're looking at the size of group, Q, P, within group P, not the size of group Q within group P, which would be nonsense.
This is what it means to take the property on the right-hand side as given. It means you know you're working only within the group of things that have property P. When you constrict your focus of attention to see only this smaller group, many other probabilities change.
If you're taking P as given, then P, Q, P, equals just P, Q, at least, relative to the group P. The old P, Q, the frequency of things that have property Q within the entire sample, is revised to the new frequency of things that have property Q within the subsample of things that have property P. If P is given, if P is our entire world, then looking for Q, P, is the same as looking for just Q.
If you constrict your focus of attention to only the population of eggs that are painted blue, then suddenly the probability that an egg contains a pearl becomes a different number. This proportion is different for the population of blue eggs than the population of all eggs.
The given, the property that constricts our focus of attention, is always on the right side of P, Q given P. The P becomes our world, the entire thing we see, and on the other side of the given P always has probability 1, that is what it means to take P as given. So P, Q given P, means if P has probability 1, what is the probability of Q?
Or if we constrict our attention to only things or events where P is true, what is the probability of Q? The statement Q, on the other side of the given, is not certain, its probability may be 10% or 90% or any other number. So when you use Bayes' theorem, and you write the part on the left side as P a given X, how to update the probability of A after seeing X, the new probability of A given that we know X, the degree to which X implies A, you can tell that X is always the observation or the evidence, and A is the property being investigated, the thing you want to know about. The right side of Bayes' theorem is derived from the left side through these steps.
P, a given X, equals P, a given X. P a given X equals Px, A, over Px. P a given X, equals Px, A, over Px, A, plus Px, not A. P a given X, equals Px given A, xPa, over Px given A, xPa plus Px given not A, xP not A.
Once the derivation is finished, all the implications on the right side of the equation are of the form Px given A, or Px given not A, while the implication on the left side is P a given X. The symmetry arises because the elementary causal relations are generally implications from facts to observations, for example, from breast cancer to positive mammogram. The elementary steps in reasoning are generally implications from observations to facts, for example, from a positive mammogram to breast cancer. The left side of Bayes' theorem is an elementary inferential step from the observation of positive mammogram to the conclusion of an increased probability of breast cancer. Implication is written right to left, so we write P, cancer given positive, on the left side of the equation. The right side of Bayes' theorem describes the elementary causal steps, for example, from breast cancer to a positive mammogram, and so the implications on the right side of Bayes' theorem take the form P, positive given cancer, or P, positive given not cancer. And that's Bayes' theorem. Rational inference on the left end, physical causality on the right end, an equation with mind on one side and reality on the other. Remember how the scientific method turned out to be a special case of Bayes' theorem? If you wanted to put it poetically, you could say that Bayes' theorem binds reasoning into the physical universe. Okay, we're done. Reverend Bayes says. You are now an initiate of the Bayesian conspiracy.